Welcome to our Tech Talks at Rocket. Rocket Reloaded is an Interreg 5A project which focuses on Dutch-German cross-border cooperation. And why do we do these webinars? Now, we want to introduce you to the innovations emerging in Rocket Reloaded's projects and the experts behind them. Today, our guest are the innovators behind E-NanoPrint-Pro. But first of all, I would like to hand over the screen to Alex van Geltrop. He's the project manager from the lead partner. And yes, the stage is yours, Alex.
Yes, thank you, Hendrik. And I also sent you a different slide. Yeah, thank you. So welcome, everyone. My name is Alex van Geltrop, and I work at Regional Development Agency for the Eastern Netherlands, Oostenrijk. And as Hendrik mentioned, I'm the project manager for Rocket Reloaded. And just as a bit more background information, Rocket Reloaded, or Rocket, is a cascade funding project, which means that we've been able to finance a number of innovation projects within the framework. It's financed in general by the Dutch-German Interreg program, and its main goal is to stimulate developments for innovative products or services that are made possible by advancements in key enabling technologies. And importantly, to stimulate Dutch-German collaboration between organizations. So in general, Rocket is coordinated by 4 core partners. On the German side, that's the Nano-Micro Werkstoffen Photonica cluster of North Rhine-Westphalia, NMWP, of which Hendrik is a member, and the Transferagentuur Fachhochschule Münster. And on the Dutch side, those are High-Tech NL and Oostenrijk. And we also collaborate with our associated partners, Innospellig, Novity, and the Development Agency of Brabant. And together with that club, we've been able to stimulate and partly finance 6 innovation projects. And those projects are in front of you on the screen. And today we are here for the E-NanoPrint-Pro project, or the ENP platform. And Marcel de Grote and his colleagues will be elaborating on that later on. But the E-NanoPrint-Pro program was originally a feasibility study within an earlier program, and is now developed into a full, mature, more comprehensive innovation project in the past 2 or 3 years. So we're looking forward to see what they've been able to accomplish during the time frame. Perhaps interesting for some of you, next week there will be another webinar on another project, on the skin ball project, which focuses on the development of a hand scanner for improved early detection of skin cancer through RF technology. So for those of you who are interested, on the same day, the same time frame, next week, that webinar will be held. And 2 other projects have already been finished and presented their results earlier on, the Automass 3D and the Sensitive program, and those webinars can be rewatched on our website, rocket-innovations.eu. I have one other issue that I would like to address. The core partners developed the framework of Rocket in order to create an instrument that could stimulate certain innovative ideas. But we were only able to do that successfully because of our connections with innovative companies and their inputs, roadmaps, challenges, etc., to help us build that framework. But in return, a lot of those companies were able to participate within the projects because the frameworks were already tailored logically to their needs, challenges, roadmaps, etc. So in general, the invitation that I would like to extend to everybody listening is that if you're part of an organization that has ambitious, innovative goals for the coming years, feel free to reach out to either me or one of our colleagues in this webinar. And we can get acquainted, discuss ideas, and see if we can support each other on the short or middle term and see what is possible, just like we did with the 6 projects in front of you. That's it from my side. I hope that you have an informative, useful and enjoyable webinar, and that you enjoy the day. So Marcel, Arjan, Hendrik, feel free to take over.
Yeah, so thank you very much, Alex. And now, Arjan, if you would like to share your screen, you can start your presentation.
All right, let me share our screen here. Just a moment, please. I think that should work now.
Perfect.
Okay.
The screen is yours.
Thanks. Thanks for the introduction.
Well, excellent. Welcome at this Tech Talk by DoMicro, and let's say having the opportunity to chair this project. My name is Marcel Goten, and next to me is Aart-Jan Hoeven, who has contributed as a partner into the project. We are extremely grateful for, let's say, setting up the structure of Rocket and the interregional collaboration, and especially by support by Alex and Henrik in setting up this kind of projects. And as Alex already indicated, this program and this project, development project, was a continuation of the feasibility study we did before this project. And actually, the feasibility was initiated by discovering the electrospinning technology as being one of those emerging technologies that could be applicable for microelectronics applications. And this triggered the feasibility study. And after the feasibility study, with some let's say, literature and also some benchmarking and doing some laboratory experiments, we created this project together with our partners in Germany, Microtech and Cotema, for developing the next step from, let's say, feasibility into functional modules and into a prototyping activity. And this is what we're going to present in this presentation. Maybe can you give the next slide? So as I told before, so the German partners Microtech and Cotema contributed into this consortium together with Tech2Biz, which is in fact is Aart-Jan's activity, and also TechV, which is a system designer specialist within our network in the high-tech Brainport region in Eindhoven, and then being supported by Alex and Orsenelp and others, giving really tailwind in financing this innovative activity. Here you can see, let's say, the consortium as such. So we had the honor to lead the program. The Microtech typically is a specialized company in Duisburg on 3D structures and manufacturing of microsystems. Cotema is this innovative company on roll-to-roll industrialized equipment and having an R&D center in Dormagen. And Tech2Biz, which is Aart-Jan, in fact, is specialized in international project management and also has a lot of experience in market analysis and development in display and semiconductor. And as last but not least, TechV, which is actually a specialist on arm's length from DoMicro, responsible for design and engineering of systems and printer systems. So with this consortium, we addressed the project and the program, and so continuing, I can tell you a little bit about E-NanoPrinting, why we were embarking upon this technology, what we needed to do to create a solution for that, what we have learned and what results were yielded from the project up till now. And obviously we can close with the perspective and next steps for future developments. Now the E-NanoPrinting project and the feasibility study actually was about embarking upon electrospinning and electrospinning creating nanofibers or nanowires. And as I learned in 2016 on a conference, the nanofibers, the nanowires as being generated by electrospinning technology was already studied in research for about a decade. I learned about this technology only recently, let's say, converting nanoprinting for other applications rather than research. So It could be used for batteries or in photovoltaic applications. There is a room for, let's say, nanofibers also in display and in microfluidics. So in general, also for electronics and semicon, nanofibers obviously are, of importance. And last but not least, even in biochips, I've seen a presentation, and you can see the image for that even nanofibers, which are useful for being scaffolds in cell structures, also could be used for interconnection with our nerve systems, and in future could then be a connection for bioelectronics stimulation. Now, the nanofibers could yield and could be a structural components for filters or membranes in these applications, and also could be applicable for touch screens, micropumps, or even microelectromechanical systems for that. Now, within this study and within this development, we particularly focused on the red sections, as you might conclude, on touchscreens and micropumps. And these were, let's say, the application areas where our German partners in the consortium have a special interest. And if I look into the touchscreens capability, then transparent conductive film is of paramount importance into this, let's say, high volume industry. Creating transparent conductive films in the incumbent technology currently is indium tin oxide, as you can see in the middle. And the industry is looking for replacement of ITO, as indium is a scarce and rather expensive material. And so if there would be an opportunity to replace that with metal mesh, it really would, let's say, enhance the performance of transparent conductive film, and it would lower the cost. So there is a large driver for finding alternative technologies for ITO replacement. And metal mesh would be, let's say, the application to go for. And nanoprinting could be one of those additive technologies to create metal mesh. So here we go. These are the applications we are trying to follow through. And next slide, please. This is what I just, let's say, tried to explain. There's a large potential on transparent conductive film, the replacements of ITO, and creating large area capability also, let's say, from a performance point of view. Next slide will also indicate the second key application, which is in fact the micropump for biological and inside medical body implementation. So Microtech already had developed a prototype for a microfluidic pump based on this, let's say, wires structure, as you can see on the picture. And the ambition would be to create a very small pump, a very small pump that could be feasible if we would be able to print microstructures or nanostructures, even submicron structures, yielding a pump functionality. So this is the second key application the project was focusing on. Now, the electrospinning technology actually is also called electrohydrodynamic printing. And the electrohydrodynamic printing, in fact, is a near field electrospinning. So regular electrospinning technology, which already exists for about 100 years, was used for, let's say, creating fibers, and typically having a distance from the needle tip to the substrate of about 300 millimeters. If you spin on 300 millimeters distance at high voltage, let's say 30 kilovolts, you get a randomized fabric. But if you bring the needle tip close to the substrate, like 1 millimeter, and reduce the voltage to, let's say, 1 to 2 kilovolts, you are able to pull a fiber from the so-called Taylor coil from the needle tip onto the grounded collector. Now, this voltage then only works if the polymer solution is not conductive. So it should be able to have a ability to repulse electrostatically, and by doing so, elongation of the fiber. So this is the way the fiber is being pulled from the needle tip onto the grounded collector. And then several parameters are influencing this technology or this phenomena, like the viscosity of the polymer solution, like the height, like the electric field strength, but also the speed difference between, let's say, the substrate and the needle tip. So the higher the speed, for instance, it pulls and elongates the polymer jet from the needle to the substrate. And by doing so, you have this direct write patterning capability of near field electrospinning. And this is what we call electrohydrodynamic printing. Okay. Now, to be able to follow through on this process, you need a printer. And within the project scope, so the first step actually was to design and create a dedicated print head and driver electronics to be able to do the electrohydrodynamic printing. So what we did within this project was design and engineer the print head with the specific features, needles, and what have you, to create this jet and put that into an existing laboratory setup for printer, a Pixar LP50 setup, where we could demonstrate at least the first process results. This is what we did for creating the pump prototypes. And next to that, we also integrated within the project on a roll-to-roll environment at Cotema in Dormagen, the integration of the printhead module and the system electronics into a industrial research roll-to-roll test environment. Now, here you can see what we developed through the course of the project. So we created a first prototype module of the print head. At the left, you can see the framework and the body holding two syringes with driver motors and electronics. And you can see the red cable, which actually is applying the high voltage to the needle and being insulated from the frame. Now this high voltage is being applied by the driver electronics, as you can see on the second picture. And in red, you can see the high voltage drivers with the microcontrollers and the electronic interface for driving the motors and doing the human interface with the printer. And on the right, you can see, let's say, live the nozzle being operational with a print jet. And the nozzle is actually, in this case, we implemented a double needle system, so we can print a coaxial fluid, where in future we can implement, for instance, silver ink or silver nanoparticle inks in the core, and then apply a polymer shield on top of that to create the elongation and repulsion on the jet fiber. Next sheet, please. Here you can see what we then did, and by doing so, having a setup or prototype for a printer creating conductive wires. Now, for creating conductive wires in your application, you can follow several strategies. Well, one of those strategies is to print etch resist, or at least a polymer, on top of a metallized substrate, and then use the printed fibers as a mask for creating and then etching away the metallic film, removing and stripping the polymer layers, and you got your metallic nanowires or your metal mesh. So this would be one way of doing that. And another way of doing that would be to, and this is why we got the coaxial wires or needle, to create a coaxial stream or jet, where the silver nanoparticles would be internal into a shielded polymer. Now it's obvious that driving a silver ink or silver nanoparticles would immediately shortcut the high voltage from the needle to the substrate. So the sheet polymer should then protect this electrostatic field. Other application could be to go for conductive polymers like PDOT, PSS, or even using a solution where we could have a precursor and having a post-process by treatments and creating the metal mesh later on the substrate. So these process variations are typically to be examined and to be explored by the EMP printer. And during the course of the project, so after actually establishing this prototypes, we did some experiments. And here you can see some results, some nice results with PoE on copper substrates. And we could demonstrate functionality of the tool, having line width of 20 micron in this respect, with spacing of 100 micron. And controlled on PET also the line width. And we did actually a parameter study like a DOE on several parameters which are influencing the diameter dimensions, like flow rate, as you see in the top screen, and also the electric field strength, and finding optimal parameter sets for the printing process. We also did some initial tests with conductive wires, so with the coaxial spinning, but we only are at the start of doing, let's say, this exercise, as the search for applicable silver nanoparticle inks is still ongoing. For the industrial application, as we're indicating, for transparent conductive film, creating metal mesh, we did the experiments with the Cotema's smart coater and implemented our prototypes for the printer, the needle and the driver system on top of and integrated into the coater. And then studied, let's say, functionality and understood about the parameter space to be explored. And here you can see, you know, applying this printer head on top of a slide or a transfer slide, we could create the first, let's say, zigzag patterns on a web, and you know, giving the first feasibility on creating nanofibers on roll-to-roll applications. For the micropump fabrication, we first started to print by inkjet printing the corresponding lines to see if we could just, you know, miniaturize the pump. We still need to explore the electrohydrodynamic printing in feasibility. Now to also explore the miniaturized functionality of the pump, Microtech also did the experiments with PVD and etching, so lithographic processes, to understand the characteristics of a micropump by doing this, let's say, fine feature structures in this respect. So that's what we ended up with so far within the project. And this brought us to, let's say, the results of the and learnings of the project, where the e-printer prototype has been successfully made and was functional. So we demonstrated stability in driving the near field electro spinning process, so the electrohydrodynamic process. We were able to create the samples and do a process study. You can see in the picture right, we also were able to demonstrate not only, let's say, 12 micrometer feature sizes, but also we were able to make submicron wires demonstrated, as you can see on this picture. We did the trials with the integration of the printer modules in the smart coater of Cotema and showed that the system is functional and we will be able to move into next steps for industrial applications. For the microfluidic pumps, we created together with Microtech a batch of pumps to be characterized and fabricated. And these are still under test and learn about next steps which we need to do to develop the pump into the next revision of innovation. And it's clear that the project was a really support and boosted the cross-border cooperation, strengthened our, let's say, network, and brought together our gained insights or our mutual perspectives in market and in technical capabilities. So I already concluded on that. The e-printer now has the maturity that we would be able to also perform studies on materials or even making this printhead and electronics available for research labs or environments. So within the course of this year, we are working on making a series of about 5 of those heads, which then could be incorporated into motion platforms or in printers like the LP50 and making that available for industries or for research institutes to do their own material research. The application of this printing technology, near field printing or electrohydrodynamic technology, is clear possible within roll-to-roll application as we demonstrated. And as stated before, we have a clear view on the development for, okay, what next steps we need to do to create a microfluidic pump by this nanoprinting process. So that's, let's say, to go short, an overview about our project. If there will be any questions, we will be open to answer, and we would welcome to learn about your, appreciation.
Yes, thank you very much for your presentation. And now I would say we can open the floor for questions. So if you have any questions, you can type them into the chat, or otherwise you will find the function reactions, and there you have the function raise hand. As soon as you raise your hand, we will see your icon, and then we can hand the mic to you. Ah, okay, Willem Endhoven, you're fast.
Thank you, Marcel, for your explanation. In your last slide, you referred to next steps with the making the device for labs and knowing a technology roadmap that is realistic. If I cut things short and I say, what is the first volume application where you're hoping for? Who should now jump up and say, we must talk?
Yeah, good question, Willem. Thank you. Well, in principle, the killer application for this technology would definitely be the touchscreen, so the transparent conductive film application. And this is also where we work together with Cotema to further explore, let's say, integration capability on their roll-to-roll equipment. But it's clear that to step into this development, it's not a Friday afternoon activity. So this really would need, let's say, next level system engineering and development to create a total solution, which would be, let's say, to be implemented in industrial environment at the end of the day. And for doing so, there would be a need, obviously, for a launching customer, or at least let's say, an applicant in industry would say, okay, we really want to go this route, okay, and we really want to team up with Cotema and DoMicro to put this effort together into place.
Yeah, clear. Thank you.
Okay, and we already we have a question to the in the chat. So, did you investigate optical properties such as polarization of the wires?
Yeah, good question. No, not yet, indeed. This would be, let's say, next steps to go. So, based on research, actually from Dow, where we connected in the early days and also learned about this technology from them, they did studies on haze and transparency based on silver metal mesh, which they researched on this technology. And they showed pretty high capabilities, like 1% haze, 95% above 95% transparency of this fibers. Now the fibers can be as thin as 1 micron or below. And as far as I understood in discussions, to be invisible, you should create fibers below 3 microns. So it really, it will be avoided by naked eye. But these are the properties I'm aware of as being done in research mode in those days. But we have not been able to find the proper inks yet to create this metal mesh in the same way yet.
Okay. Did this answer your question? I think yes. Or have you further questions? Partially. Okay, let's keep in touch. Sure. Okay. Yeah, I hope so. Okay, perfect. But okay, so yes, Dirk Kalinowski raised his hand.
Only one question. You've mentioned always the silver as your material for the nanowires, and that you started with that. Do you expect that is also possible with gold or other materials, or what do you need for that? Is it a material that you produce by your own that you need for your printer, or is it something that you buy?
Okay, Dirk, thanks for your question. Well, actually, silver inks are quite available on the market in printed electronics. I might have forgotten to introduce DoMicro in that respect. We are a company, let's say, a technology company in printed electronics. So we are pretty familiar with the flexible hybrid electronics industry and also supply chain. Silver inks are abundantly available from several brands. Silver is a nice material since it's not so costly, and you can handle with that in atmospheric circumstances. So you don't need, let's say, high temperatures or nitrogen environment or inert environment to treat. So it's a very friendly material to work with. Sure, there is other materials as well, like there are also copper inks available, but then you really need to take care about the oxidation problems with nanoparticles of copper. The gold is going to be more expensive to give, and we even have platinum ink, nanoparticles platinum ink. But that's extremely expensive, actually. So silver is a moderate, abundant available material which can be applied for this applications. We don't formulate our inks ourselves, so this would be something to reach out for and see if we can find, let's say, partners to collaborate with and find appropriate materials to do this nanoprinting process.
Okay, so you're so far into. Oh, Alex van Geldrop has also a question.
Yeah, thank you for the presentation, Marcel. You mentioned in the beginning that for transparent conductive film that the best alternative material would be metal mesh, which is the one that you're currently working with. I was wondering, are there competitive methods of people trying to integrate it, or is there really at this point no one else that has a serious idea to integrate this material within the conductive film?
Well, yes, there are competitive approaches. I've seen competitive approaches in industry. It would be quite bold to state that this would be the only way forward. I don't think that's the case, because the search for transparent conductive film with high properties in terms of conductivity, transparency, and low haze is already ongoing for a couple of years, trying to replace ITO. So yes, there are. I have seen several other technologies that could, approach this quest. Now, the benefit of electrospinning actually is that it's atmospheric, so you don't need, let's say, high costly vacuum tools. It's direct write. It's fast. Let's say pulling the jet can go up till, let's say, a high speed, like 5 meters per minute or so, or it can go pretty fast. So it is, let's say, an inexpensive, straightforward application or additive technology, which could yield, a direct write solution, which is promising for this application.
Thank you.
Okay, so I think the fact that you don't need a vacuum and that the printing speed is quite high, I think it's very interesting, for example, also for demonstrators and prototypes, also in industry, not just for research purpose. That's right?
Yeah, that's correct. That's correct.
Okay, great. But how could people obtain a printer?
Well, straightforward to please contact us and let's collaborate. We could start off with do the application development and process research together, for instance, on our setup, which we have right now. And next to that, having a launching customer for, let's say, the first series of print heads and electronics and systems would be very welcomed, and then we can just leverage the design and engineering and also sales and services for this printer and printer modules to be integrated. So we do have the capability to not only, let's say, research the technology as we showed or design prototypes, but we also could follow through within our network in terms of the making available print heads and driver electronics to be integrated, or even integrated together with, let's say, a customer making platforms available.
Okay, and I think the network is a very interesting point because, for example, in your consortium, there's also Cortema, and they have this technicum. Yeah, so for example, they have the machines and you can test to find a suitable solution, because I think the printers should be configured very individually for each application field. Okay, and what's the time frame? If I say this is a nice idea, how long would it take to develop your technology further for a certain application field?
Well, I think that during the course of this year would be feasible. We're about to set up the design and engineering of a first series of print heads. Let's assume that would be projected to be ready by mid of this year. So we could be second half of this year. We could embark upon, let's say, market introduction and collaboration. So this is what we are aiming for.
Mm-hmm. So while Rocket Reloaded was an Interreg 5A project, I think Interreg 6A is about to start. So this could be, for example, a good contact point in the end. Okay.
That would be great, Hendrik. We definitely would appreciate the support of Rocket 6.
Yeah. Okay. Are there further questions? Oh, thank Can you say something about the benefits of the electrospinning technology over conventional printing technologies with conductive inks, for example, circuit boards?
Yeah, sure. Good question. You know, the current printing technologies are typically related with, you know, the spitting or drop-on-demand system, so like print heads, okay? And for print heads and inkjet printing, or even, let's say, other technologies for printing, it's very hard to go below, let's say, 30 micron resolution or feature sizes. That's almost not possible. So about the inkjet printing process is limited in terms of accuracy and feature sizes. So to go into the area of semicon, let's say advanced packaging, where you need to have feature sizes, you know, somewhere between 1 micron or 10 micron, okay, to implement like redefinition layers in advanced packaging or interconnection of chips going to the contact pads. You cannot do that with, let's say, conventional inkjet printing or screen printing. You cannot do that either because, you know, it's not direct write, it's not digital screen printing. So here are the limitations of conventional printing technologies. And with this direct write nanoprinting, we try to break through this barrier and move into the range of 1 to 10 micron or even below 1 micron, depending on applications. So instead of pushing a droplet out of a nozzle, pulling to the droplet and creating a nozzle and creating a jet, which is sub-micron or micron dimension.
Yes, and as you already mentioned, the faster you go, the thinner your print lines will be. So
right.
it's getting even smaller and thinner. Okay, great. Further questions? Okay, the last question was answered. Okay, this is great. But do you have any further questions? Okay, I think this is not the case. So I think I will send a follow-up email, and I can put your contact into this email so that if there are any further questions in the future, that they can contact you. Yep. And we will also publish the video later on. I will also put the link into this email so that all of you, dear participants, will have the information of this webinar, and possibly there are ideas about application fields. I think this is the main, most interesting point for this project and for the consortium, to find some application fields, and let's test this technology, what it really does. Yeah, so again, thank you very much for this very nice presentation about the innovation you achieved in this project, and thank you, dear participants, for your interest. And as Alex already mentioned, maybe we will meet again next week. Then it's about skin cancer detection by photonics. So thank you very much. Have a nice evening, and hope we will meet soon.
Thank you, Henrik. Bye-bye.
Thanks a lot.
Bye-bye.
Thanks a lot. Bye.
Bye-bye.
Thank you. Bye.
Good evening.